in the normal condition, let this is the power angle curve in the normal condition. We do not know the steady state stability limit in the normal condition, but it is said that the generator is delivering 1 per unit power. It means the prime mover input is 1 per unit, and it is also said that the generator is delivering 1 per unit power at the power angle of 30 degree. So, this 30 degree, this is the power angle at which the generator is delivering power of 1 per unit in the normal condition. We know that at this 30 degree, this electrical power output of the generator is equal to prime mover input of the generator is equal to 1 per unit. Using this logic, we can say that the maximum power, the PEM value in pre-fault condition will be 2 per unit. If the maximum is 2 per unit, then only the output value, the electrical power output of the generator will be equal to input equal to 1 per unit at 30 degree. So, using this two data, we can calculate the maximum power steady state stability limit of the system in pre-fault condition equal to 2 per unit. And it is also said that after the fault condition, after the fault happens, the steady state stability limit of the system drops to 0.4 per unit. So, this is the power angle curve during fault condition, in which the steady state stability limit is 0.4 per unit. And also it is said that after clearing the fault, the steady state stability limit of the system becomes 1.5 per unit. It means this is the power angle curve of the system after clearing the fault. So, we have three power angle curves. This is power angle curve in pre-fault condition, the maximum value is 2 per unit. This is the power angle curve during fault condition, the maximum value is 0.4 per unit, and this is the power angle curve in post fault condition after clearing the fault, and the maximum value is 1.5 per unit given in the problem. We have to find the critical clearing angle for this system. So, we know that corresponding to the critical clearing, at this point the system is operating prior to the fault. Just after the fault, this operating point will shift to this during fault condition, and after that the generator will accelerate, the rotor angle delta will increase, and after some time the fault will be cleared. We have to find the critical clearing angle. So, we will assume that we have cleared the fault in a critical condition, so that after clearing the fault, the system, the operating point shifts to the post fault condition, and after that the machine deaccelerates to find the synchronous speed once again at this critical point. So, the machine has synchronous speed at this point and synchronous speed at this point. So, corresponding to the critical clearing, the machine will attain synchronous speed at this critical point. We can find this critical point, the angle at this critical point delta 2 max by we know that if this is angle theta, then this angle will be 180 minus theta. So, what is this delta 2 max? It is simply 180 minus sine inverse 1 upon 1.5. So, what is this delta 2 max? We have calculated this delta 2 max. It is equal to, so we have calculated all the angles. First we will find the accelerating area A1. What is this accelerating area? This is accelerating area A1 shown in this is accelerating area A1, and this is deacylating area A2 max. In critically stable condition, A2 max is equal to A1. How we have calculated this area A1? How we have find this area A1? This area A1, oscillating area A1, is simply the area under the PM curve minus the area under the PE curve between the two angles at which the rotor is accelerating, and this deaccelerating area A2 can be found by finding the area under PE curve minus area under the PM curve between the angles at which the rotor is deaccelerating. So, this is area A1 and this is area A2 max. Since the speed at this point is synchronous speed, and in critically stable condition the machine attains synchronous speed at this critical point. So, the speed is synchronous and again it attains synchronous speed at this point. It means that this area, this oscillating area A1 will be equal to A2 max. So, in critically stable condition we can use A2 max equal to A1 to find the critical clearing angle. What is this A2 max? It is simply 1.5 sin delta, this is PE minus PM, which is 1 d delta. To find this A2 max we will integrate over delta CR to delta 2 max, which is 138.2 degree. To find this area A1 we will integrate PM, which is 1 per unit, minus PE 0.4 sin delta d delta, and we will integrate it over angle 30 degree to delta CR. Using this relation we can find the value of delta CR. It will be equal to 67.35 degree. So, this is the critical clearing angle in this problem.